we've been on this topic for two days. That's longer than I usually do, but that's fine. So we were looking at random variables and so on, right? So the idea behind a random variable is, or a distribution. We were looking at distribution. So a statistical distribution is something that can produce a sample, and the sample is usually a random variable, or it is a random variable, which means that it can take any value, but some values are more probable than others. So, and that probability distribution is specified in that statistical distribution. We looked at many distributions last time, right? We looked at Gaussian, we looked at Bernoulli, binomial, and so on. And we'll come across these again and again later on, right? Then we looked at some properties of distributions and properties of random variables. Things like if you have two random variables with two different distributions, how do we compare them, or how do we look at them together, right? So that's called joint distributions, and there are notions of covariance, correlation. These things we looked at last time. Looked at multivariate Gaussian distribution. So this is when you have many. If you have many Gaussian random variables, you stick them together in an array, you can model it as one vector, right? So your random variable is now a vector of observations, and then this is the PDF for that. So we looked at all of this, right? One quick thing that I wanted to talk last time was that another way to understand random variables and distributions is using concepts, notions from information theory. So we'll come across these later on. So I'll quickly go through some of these properties. We will not, spend any time on this, but later on when we have to talk about it, I'll discuss it in more detail. So, and I'm sure you know some of these. So the notion of entropy, right? Entropy in general tells you what is the sort of chaos in the system. So if there's low entropy, means that everybody is balanced, right? So if it's high entropy, means you have too much variation. So you can think of a random variable in that way. So if a random variable takes 6 values and all of them are equally likely, right, then your entropy will be low, right? Sorry, entropy will be high, because anything is possible. But if your random variable takes only 1 value and everything else probability is 0, then your entropy is low, because you know it's going to be that value, right? And then there are other notions within information theory that we'll look at, things like how to compare two distributions, right? How to compare two distributions. There are measures like Kullback-Leibler divergence or KL divergence, which has a mathematical formulation, so it's nothing vague. It's pretty precise, and we'll look at that later as well. And other notions like mutual information. So last time we were looking at correlation, right? Correlation was one way of saying, okay, how much do these two random variables vary with each other? So if you're looking at height of people and weight of people, then those two random variables are expected to be correlated. Somebody is high, somebody is tall. You can say with good confidence then that the person would have greater weight as well, right? So that's a notion of correlation. But many times correlation is not applicable. For example, if you have discrete random variables, right, then you cannot define a correlation. In those settings, we define something called mutual information. So mutual information has a similar idea as correlation, which is if I know something about one of your random variable, what do I know about the other, right? So if they are perfectly aligned, then it's easy, right? If the relationship between weight and height is 1-to-1, like whatever is the weight, that is the height, then if you know the weight, then you know the height, right? So there is a high degree of mutual information or high correlation. But if it's not, then it's low. So mutual information is another way to look at it. All right. So this is sort of the conclusion of all of this random variables and distributions. And if you're interested, you can pick up any one of these books or any other book that you like, and you should be able to see these things. All right. Any questions so far? All right. Good. So now we are going to move to the real interesting part, which is how do we use the notion of random variables and distributions to learn, right? Because this is a machine learning class. We want to learn from data. So we'll look at that today. All right. So this is sort of, so one type of machine learning models that fall under this statistical machine learning is what we call generative model. So I'll tell you why we call them generative, but this is the idea. So let's go back to our tumor example, if you remember from first week, right? So we have data which is represented using X, which tells you things about tumors, and what you want to predict is y, which is this a tumor or not? So that's your class, right? So for now, let us assume that x is essentially, or actually in our example, x was a vector, right? We had bunch of variables. We had size, and we had shape and color and smoothness and so on, and each one was binary, right? So you can think of that vector. That vector will also be discrete, right? Because it consists of discrete entities inside. So each vector, you can only have discrete possibilities for that. So x is still a discrete variable. And what we want to find is that when I get a new x, a new input, I want to find what is the probability of y to be c. Now this is slightly different from how we formulated the problem in for the other type of algorithms like neural networks, where we directly wanted to find what is y. The question we used to ask was, what is y? Is y a tumor or a malignant or benign, right? But in this case, what we want is, we want to build a probability distribution over all possible values of y, okay? So y can be benign. So what is the probability of y to be benign? What is the probability of y to be malignant given x, okay? And then whichever is higher, you choose that. So in probability or in statistical machine learning, the core idea is that everything is possible. All right, everything is possible, but some things are more possible than others, right? It's like Animal Farm. So what we want to do is, we want to find out each probability and then figure out which one is higher, which one is lower, right? And of course, we have seen Bayes' rule, so we can do that this way. So let's say theta is the set of parameters that are associated with our model, which will vary for different models. But the idea is that the probability for y to be any class, so benign or malignant, given x is something, can be written as this, right? And you will note that I've put a proportional sign here, because what I've done is I've omitted the denominator. Because the denominator, if you did the gradients puzzle, gradients quiz last week, you would have seen that the denominator is the same, right? Because in denominator, we essentially marginalize over all c's, so it doesn't matter. So what we want is, we want to find this quantity, and this is proportional to this value, okay? And the problem will be that this will no longer be a probability, because the values won't sum up to 1, but that is fine. We just want to find which one is higher, right? So we don't really care about the denominator for this time right now, right? So here is what we want. We want to find what is the probability of x given the class is c, and then we want to multiply it with what is the probability of y to be c. So this is what we call the prior. So this is, you can think of this as, without even knowing what x is, what is our belief that y will be the certain class, right? And this is what we call the evidence. So this is, we see this, right? We observe an x, and now we want to see what is the probability of that x. And using that, we want to compute this, right? So this, if you look at this value and the last one, they have similar form, right? They are both trying to tell you the probability of y to be c, right? But here we are not using x, here we are using x, right? So this is called the posterior probability of y, because this is after we have observed. So before we observed it, this is what we had, right? If I don't give you data, all you can say is that, okay, in the past, probability of somebody having a benign tumor is 0.9, so that's the probability, right? But then once you observe x, then you multiply it with that, and that gives you the posterior. All right, so now what do we need to compute this? We need these two quantities, of course, right? This is of course the prior. This is something that comes from outside, so we'll worry about this later, but let's focus on this quantity. So this is what we call the class conditional density, right? So you can think of this as, what is the probability that x will take a certain value x when its class is c. So you can think of it as, you have two different distributions, one for benign tumors and one for malignant tumors, and you want to basically compute the probability for x, right? So if you can also write it like this. So this becomes either the PDF if x is a continuous random variable, or it becomes a PMF if it is a discrete random variable, right? So the idea is that if we can compute this, then we can compute this, right? So this is basically what we will do. All right, any questions so far? So now let's look at this. We're going to take one step back. Okay, so we are going to come to this later on. This is basically our naive based classifier that we'll look at in 2 or 3 classes. But before that, I want to, just to get our concepts a little more solidified, I want to talk about Bayesian concept learning. Right? We did concept learning earlier in this class. Now we want to see how can we do that in this statistical framework. Right? So if you remember, a concept is nothing but some function that assigns labels to your examples, right? So it can call something belongs to the concept or does not belong to the concept, right? And then it uses x, which is your input, to do that. And we want to find this probability. What is the probability that y belongs to the concept, or the object belongs to the concept, given x is x, right? So let's see how to do that. All right. So we are going to do a simple example right now, okay? What I'm going to do is, we are going to take a very simple setting. We are going to assume that our x's are just numbers on a number line. In fact, we are going to assume that they are between 1 and 100. Right? Let's say all of our data, our x is between 1 and 100, all right? And these x's have been labeled by some concept. We don't know what that concept is, right? We need to find that out. And what we have is a hypothesis space that contains our concept, right? So we want to find out what is the best hypothesis that would have labeled this data, right? So this is exactly like what we did in our class earlier, which is how do we search and find the best hypothesis? But here we are going to do it in a more statistical fashion, all right? So I need your help here. So what we are going to do is, instead of implementing an algorithm, let us try to see how we as humans would do this, right? So the problem is this: there are some hypotheses in our hypothesis space, and we need to figure out, given some data, which hypothesis would have labeled which is the true concept. All right, so to do that, I want you to go to a website. So if you have a device that allows you to go to a website, so basically a laptop or something, just go to http://b.socrative.com, and if you don't, that's fine too. You're just going to miss all the fun. So if you go to b.socrative.com, what will happen is, it will ask you to do a login, and then you should choose a student login. So go to b.socrative.com and choose the student login here. And then here just type UBML17. So UBML17. All right. So when you join this class, it will just take you to a web page where you will wait for an activity. So I'm going to give you an activity to do. So just go there, b.socrative.com, then UBML17, and I'm going to log in as an instructor. All right, so I'm going to give you a short question, right? So this is the problem. The problem is that I'm going to give you some hypotheses here. So these are the 10 hypotheses in our hypothesis space, okay? This is a very simple hypothesis space. It has 10 hypotheses, 1, 2, 3, 4, all the way to 10. So if you look at each one of them, it is kind of like a function that will take a number between 1 and 100 and either call it belongs to the hypothesis or does not belong, right? So the first one is even numbers, which means that anything that is even will belong to will be part of the concept, and if it is not even, then it is not part of the concept. Same way, odd numbers, squares, powers of 2, numbers between this, all numbers. So this will call everything. This is our most general hypothesis, right? Calls everything as part of the concept. Any questions about it? All right. So the first thing I want you to do is that without any data at all, right? So I'm not showing you any data. Can you tell me which one is the right hypothesis? So in this case, of course, it's a random guess, right? Because we don't know anything about which one would be most likely hypothesis. So it would be a random guess. So why don't we do that? Just take a random guess between 1 and 10. So enter a number between 1 and 10, where each number corresponds to the hypothesis, whichever you think, whichever you like, right? Just by your prior experience, say, hey, I'm going to choose this. So just enter a number between 1 and 10 when I do this, of course. All right, go ahead. Start entering numbers. Yeah. All right. So this is basically all of you are inputting numbers. Somebody inputted 45, but and 5. But this has to be between 1 and 10. But that is fine. We'll ignore that. And that is the thing about probability. Statistical machine learning is that anything is possible, right? There's no absolute answer. It's like Revenge of the Sith, right? Obi-Wan Kenobi says that only the Sith believes in absolutes. Everybody else believes in probability, right? So let's do that. Okay, so I think I've got enough answers. So let's finish it. And then what I do is there's slightly cumbersome process here where I download it. It goes here. Maybe one of you later on can create a better system. This system is more meant for like an online clicker, so it's not. So I load it. Of course. So this is what I get, right? I ignored the silly answers, but this is the distribution. So let's. I hope I can make it bigger. All right. So these are the different. So you can think of these as probabilities. So each one of you is part of this collective machine learning algorithm. And what you did was you said that, this is what we think are the probabilities associated with every hypothesis, right? And because we didn't know anything, you will see that, it's kind of distributed. Maybe you didn't like the hypothesis number 9 for some reason, which is fine. But that is the idea, right? Okay, so now what we are going to do is I'm going to give you some data. So let's say 16 is our data. Okay, so now I want you to again tell the most likely hypothesis that you think out of these 10, given that you have seen this. This is our training data. That's number 16. Okay, so just off the bat I can tell you that multiples of 5 probably won't be a good hypothesis because it won't cover 16. Some of them will, right? So let's see what you do in this case. So I have to start a new shorthand. All right, so let's go ahead and choose the most likely hypothesis, knowing that 16 is our data set so far, right? So the dark side, right? All right. All right, so let's stop here. All right. All right. Okay, so now I'm going to do the same thing. I'm going to plot the distribution, and this is what we call an empirical distribution. I have certain frequencies for every possibility, and then I just plot a histogram, right? So let's do that here. So what I'm going to do is I'm going to save this here so that we don't forget. So this is basically our prior, right? Without knowing anything, this is what we said would be the value. Now I'm going to load the new one. Sorry. Okay, so now what you see is that the distribution has changed a little bit, all right? And the reason the distribution has changed is that because now we know something about the data, right? So earlier, your prior was like this. I should make it a little smaller. Sorry. But anyway, so earlier our prior was slightly different, and now it is this, right? So, and the reason is because now we know something about the data. So if I can pull this data closer, right? So now what happens is that nobody thinks 8 is a right answer, right? and nobody thinks that 7, or somebody thinks 7 is the right answer. That's possibly because I said it, right? So so I'm sure that, yeah. And then, but a lot of you said that, okay, maybe the squares is a possibility, right? And then some of you said all numbers between 1 and 100 is a possibility. So right there is a very interesting observation that with this 16, right, even this is a right answer, right? This hypothesis, which is all numbers between 1 and 100, covers 16, yeah? And squares also cover 16, but it turns out that more of you preferred 16 or the squares hypothesis than this one, and there's a reason for that, and I'll come to that reason. But let us, since we are having so much fun, let's do it one more time. And let's say that let's say that this is our data set. So this is our training data. It has 16, 4, 64, and 32. And now let us try to find out what is the best answer. All right. So for that, I have to start again. So remember, so this is our data set. These are our 10 hypotheses. Go ahead and find what is the right answer. One of the 10. The first time I did this quiz in class, this was 4 years ago, and I made a very simple script, assuming that everybody would put between 1 and 10, right? And then I quickly realized I need to have a sort of a way to eliminate the bad ones. All right, so I'm going to stop here and then do it again. Get report, download, and let's do it here. Okay, so this is the distribution that you get now. So suddenly the distribution has become much more like, you know, precise in some ways, right? So if we think about it, so what everyone has done is that because our data set was 16, 4, 64, 32, you said that, okay, maybe the powers of 2 is the most likely hypothesis, even though other ones are also okay, they're not wrong, right? 10 is not wrong, 1 is not wrong, but still you give more importance to this one, powers of 2, right? So now we'll see why we did that, right? So we'll jump into your brains and figure out why you make these kind of decisions, because it turns out that the machine learning algorithms that we will see also do the same thing. All right, any questions so far? All right, so so no more fun for today. I guess we just jump to what we did. All right, so the question is, why choose powers of 2 concept more over even numbers, right? And of course, some things are obvious, right? The reason that 9 is not, nobody chose 9 is because this hypothesis does not cover all of this. So it's actually plain wrong in this case, right? Some of you did choose 7 and 8 because evidently we are still in kindergarten, right? But otherwise, some of the right ones have been chosen, but some of them have been chosen more likely than others. And there's a reason why, right? The reason is because humans try to follow this principle of avoiding suspicious coincidences, all right? So the thing is that if you see these 4 numbers, right, then immediately in our head there's a flag that is raised, right? Why only these 4 numbers when you could have had any number between 1 and 100, right? So even though there are multiple hypotheses here which cover this set, but there is a suspicion in your head that definitely there is something about these together, right? And one of the ways to link them is, of course, that they're all powers of 2, and they said, hey, you know, let me choose that as the answer instead of even numbers or numbers between 1 and 100, because that one kind of explains this data more than others. It actually resolves this suspicion in your head, right? Little more. So that's the idea. So that is what you did. But statistically, what you did was that you chose the concept with the highest likelihood. all right? And I'll tell you what likelihood means here. So the point is that the likelihood of this data, okay, so likelihood is always associated with some data. So likelihood of a data under certain hypotheses is higher than the likelihood of the same data under certain other hypotheses, and we tend to choose the one that has the highest likelihood, all right? And that is what all of these Bayesian systems also do. So let's talk about what is the likelihood of this data under these different hypotheses, all right? So one thing you can see is that okay, let's go ahead. All right. So what is likelihood, all right? So if I have a data set D, then the likelihood of that data set is simply the product of the probabilities of each data point inside that data set, all right? So that is what this is. So you have a hypothesis. So likelihood is always computed for a data set with respect to something. So here we are computing it with respect to this hypothesis. So the hypothesis is that this data was generated by this hypothesis, and it is simply a product of all of these, all right? And then we all often talk about log likelihood, because this is a product, and products are a little cumbersome to work with. But if you apply log, then that becomes a sum, right? And that is easier to work with. So oftentimes you will hear me talk about log likelihood rather than likelihood, but they have the same property, right? It's just a log of the likelihood. But so what we now do is we want to find out the hypothesis which gives us the highest log likelihood, and which is simply the summation of all of these values, all right? So now let us see what is, and this was a result from last time, but what is the log likelihood of any of the data set under any hypothesis, all right? Okay, I'll fill that later. Seven, right? Did you 7? 8? All right, so likelihood. So let's say I have a data set D which has a bunch of points, right? So in our last example, our data set had 4 points. And we need to figure out the likelihood of this data set. So usually we write it like, yeah. So we can think of likelihood as just the probability of D given H, and which can be written as product of each data point probability of X given H, right? So now what is the likelihood of each data point? So here is my hypothesis space here, right? So what is the probability? So let's say we want to compute the probability or the likelihood of data set where H is even numbers, right? So this will be probability of 16 given even numbers times all the different probabilities, right? Now what is the probability of observing 16 given all the even numbers, right? So how many even numbers can there be in your data set? 50, right? Because your data was 1 through 50, and 16 is one of the numbers out of that. So the probability that you had 50 even numbers and you picked out 16 is just 1 by 50, right? So it is going to be 1 over 50 times, actually it's going to be same for all of them. So this is the probability or the likelihood of your data under this particular event, right? Now let's say what we want to see, what is the probability of D given squares? H is squares. Now how many squares can there be in your data set? Is 9, right? So 9. So it's going to be, so for 16 it is going to be 1 over 9, right? But for 4, 1 over 9. For 64 it's going to be 1 over 9. But for 32, because 32 actually will not be in that pool, right? So the probability of picking 32 from all the squares is actually 0. That will be 0. So the likelihood of the data for this particular hypothesis is actually 0, right? Which doesn't happen in real world, but this is a very contrived example. So here that happens, right? And the same way you can compute the likelihood for all of these, and then you can say that, so we can compute the probability of h powers of 2, right? Now how many powers of 2 can you have? 1 through 100? 6, right? So it's going to be 1 over 6, and each one of them is a power of 2, so it won't be 0, right? It's 1 over 6, right? So that way you can compute the probability. So what you did unknowingly is that a lot of you picked up the likelihood or the hypothesis which had the highest likelihood, right? And that is what we call in statistics the maximum likelihood estimation, right? So you want to find the hypothesis that gives you the highest likelihood, and that makes sense, right? You have some data, right? And you want to figure out what is the best hypothesis. You simply compute the likelihood of your data with respect to each one of those hypotheses, and then you pick the one that is highest. Simple, right? Any questions so far? So this is, yeah. So the question is, what if the data is noisy? And that's a good question. Right. And I guess these methodologies would still go ahead and do something, right? There's no direct way of handling that here. But then we'll look at other models later on which explicitly account for possibility of noise. So they say, okay, whatever you observe is not what the actual value is. It could have some corruption of noise, and then you can model that as well. So yeah, so that we'll look at that later. But these ones, they do not. So if suddenly in your basket, which was only squares, suddenly you had one non-square value, that will mess up the whole thing. All right, so that is that. Now, okay, now other thing. So one more thing that we did earlier, we looked at this notion of prior, right? So what you all did earlier is that when I didn't show you any data, you still gave me sort of a distribution, right? Let me try to. So this is what we got. This is sort of these are ordered by the likelihoods essentially, right? And let me pull the one that was the first one. Right. So this is what you told me about the distribution over all hypotheses when I didn't show you any data. So this is something which is prior, right? The prior information. You could pick one possibility from here, right? You could pick this one because this one has the highest prior probability, right? So that is what we would call just a maximum a priori answer, right? Which is obviously not a very good answer because you did this without looking at any data. But hey, if you didn't have any data, that is the best you could do, right? And this is also interesting, right? You gave this as the highest prior probability because this would cover anything. This was 1 through any number between 1 and 100. So that's good. And now this is what you got when you looked at when you had the data, right? So this is the prior and this is the posterior. Oh, sorry, this is the likelihood and this is the prior, right? Sorry. Sorry. So this is what you observed after you observed, and this is what was before. Now somebody could say, hey, how about combining this, right? Because this was the information that you already had, right? So this is something that's coming from an expert, and this is what you say after you observe the data. Right? What if we can combine them and find and sort of get a more reasonable answer, right? Because what this does is that this follows the data too much. Basically, whatever you saw, you immediately made some judgments about the hypothesis, right? So if the data changes, this might change, right? So this is what we have is a higher variance, right? This would change if the data changes. This won't change with data because this is fixed, right? You didn't see any data for that. So we want to come in the middle somewhere. So there is a way to combine them up and then find what we call the a posteriori estimate. So combine the prior information with the likelihood, which is using the data that you got, and then you get a posterior, okay? So this is the distribution over all hypotheses that you had before you knew anything, and then this is what you observed, and now you combine it to get posterior. So you revise it. So this is very much what I expressed here, right? So you start with a prior information about your possible classes, and then you combine it with your current observation, and then you get a posterior distribution. So in the case of this simple example, we can actually compute all of that. So in this table, I have done that, all right? So these are all our hypotheses, okay? This is the prior information, okay? So this is kind of like what you gave me earlier. Let's say it was this, right? So this is this. And then these are the likelihood of your data given all of these, for each one of these hypotheses. And then you combine them using the Bayes rule that we talked earlier, right? Using the same thing. So you want to find what is the probability of H given D, which is a posterior. That will be the same as computing the likelihood of D given H times the prior information on H. And if you want it to be probabilities, then we can also compute this this denominator, which is just a normalizing factor, right? Otherwise these values won't sum up to 1. But this, you can see, is nothing but doing this process for all of the hypotheses. So this will be a constant across all of these hypotheses, right? So then you can compute this, right? So you can think of these 3 different estimates, and you can work with either this or this or this, right? So if you work with this, what you will say is, I'm going to pick this as my most likely hypothesis, right? If you work with this, with the likelihood, you'll say, I'm going to pick the powers of 2 as the most likely hypothesis. And then but when you combine them, what you will see is that the numbers will change. In this case, this is still the most likely hypothesis according to the posterior, but it could change, right? For example, if my prior distribution was such that there was a higher value here, much higher than anything else, then this would change and maybe it would give a higher value here. So you can think of it this way. So there's a prior belief over all likely hypotheses, and then the evidence kind of tries to change it a little bit and gives you the posterior. All right? Any questions so far? All right. So how do we find the best hypothesis out of all of these, right? There are 10 hypotheses. How do we find the one that is the best? You can do it in 3 ways. One is you can choose the one which has the highest prior, which is you take this column and choose the one that is highest, but that's not very useful. We call that, actually I call it maximum a priori estimate. Others don't call it anything because it's useless. The other thing you can do is you can compute the one which has the highest, which gives you the highest likelihood, all right, of the data, which is basically this, all right? So mathematically you can say, want to find the argmax of the one that gives you the highest log likelihood. And the third one is where you compute the posterior and find the one with the highest posterior, all right? And if you think about it, I have simplified it a little bit from this one. So here I have ignored the denominator, because all you want is to find the one that is the highest value. So I just ignored the denominator, and then it becomes the sum of these 2 values, all right? So those are 3 different ways you can find the best likelihood, the best hypothesis. And then how do you use that? So now you have the best hypothesis, right? Now you get a new number. You can say, was it generated by the same concept or not, simply by applying this hypothesis on that, right? So now, if let's say we chose this as the most likely hypothesis, right? Because the posterior is giving the highest value here. So now you get a new number. Let's say it is 7. Then you can say, it is not generated by the hypothesis or by the true concept, because it is not covered by the hypothesis that we chose. But let's say you get 64, then you say, yes, it is generated by the same concept, right? So that is the idea. Okay, any questions so far? All right, so let's see. Okay, now there are some properties about these different estimators. So you can think of this, if you're coming from a more statistical background, these are different estimates, right? These are estimators of your best hypothesis or a hypothesis distribution, right? And there are some properties about this. So one thing is that if you have a lot of data, right, the map estimate, the maximum a posteriori estimate, converges towards the MLE estimate, which is basically saying that if you have a lot of data, these will become very similar. And the reason for that is, if you look at this part, right, this part, the effect of the prior is here, the effect of your likelihood is here. They are just getting added up. If your data increases, as your data increases, because this is nothing but the sum over all data points, that value will increase and it will dominate this, right? So at some point this will become pretty large compared to this, and then it will look very much like what you get from your MLE. So that is the idea. Another thing is that they are consistent estimators. That is more of a statistical concept, but the idea is that if the concept is in your hypothesis space and you get enough data, then this will find the right answer. All right. So if you have enough data, what will happen is that the distribution, if you plot it as a bar graph, the right answer will be close to 1 and everything else will be close to 0. So that is the property of these. They are consistent estimators. Clearly, the a priori estimate is not a consistent estimator because it doesn't depend on the data. Keep increasing the data, it will stay the same, right? It has no variance at all, very high bias. All right. So one last thing I want to talk today, and then we'll just before this. So what we are going to do next is that now, instead of looking at a concept space which only has 10 hypotheses, we are going to look at a concept space which can have infinite hypotheses, right? And now our question is, how do we find the right hypothesis? So if you sort of think a little more, the idea is that you express either your prior distribution or posterior or the likelihood as a objective function, and you try to find the H that maximizes it, right? So it becomes the inverse of what we did in neural networks, where we express some sort of an error and we try to minimize that error. Now we are going to express a likelihood and try to maximize the likelihood, right? So we'll do that next time, but I want to talk about one last topic here, which is now, once we have chosen the best hypothesis, what do we do? How do we use it, right? So the idea is that we get a new input x star, we can now compute the probability of y to be in this in the given concept space, given x equal to x star, all right? So for example, if you had if your hypothesis, the hypothesis that you chose was the hypothesis was the squares, right? So now you can, if you get a new number, as I said, you can compute the probability. So you can use any one of these, right? So you can choose your H prior, you can choose a H MLE, or you can choose the H max. So basically what I'm saying is that using this table, you can choose the best hypothesis. You can say, hey, let me choose even because it's giving me the highest prior, or let me choose this because it's giving me the highest likelihood, or choose this because it's giving me the highest posterior. And with each one of them, you can now figure out if a new data point belongs to the concept or not, right? That's easy. But if you are true Bayesians, right, there is one more way to do this, which we call Bayesian averaging. So in Bayesian approach, what we do is, now these three are the things that the frequentists would do. They would choose the best hypothesis. But what the Bayesians do is, they say, we are not going to choose one as the best hypothesis. What we are going to do is, we are going to assume that all of them are correct in some way, and we are going to use the probability associated with them as a confidence score. All right? So we are going to use the answer that each one of them gives, but we are going to weight it by how confident we are in them. So think of these hypotheses as experts. These are 10 experts with big beards sitting here, and each one of them can give you an answer. But each one of them has some confidence score associated with them, which is basically this posterior value. So we are going to take their answer, but we are going to weight it by their individual confidence score. So that is what Bayesian averaging does here. So if you look at it, right, so to get a new answer for a new data point, you take the answer from each one of these hypotheses. Like you say, okay, each one of them is possible, but we multiply it with their corresponding probabilities. So what is the posterior of H given D times what is the probability of X star for that given hypothesis. So this is what we call Bayesian averaging. So we'll look at that many times later on. But the general, if you ask me, Option 0 is trivial. We don't use it, but these three are used a lot, right? So this one is used whenever you're doing maximum likelihood estimation, but the problem with this one is it does not incorporate the prior. So the prior information is lost. This one uses the prior, but it does it in a way that it only chooses one expert. Says this one is the best, right? What the third one does is it takes everybody. It's like it's saying, I'm not going to ignore anyone. I'm going to hear all of your voices, right? But I'm going to weight them by what are your individual posteriors. And that is what Bayesian averaging is. So all 1, 2, and 3 are used in real life. In our discussions, we'll talk about 2 and 3 more, because they incorporate the prior. All right? Any questions so far?